Hello, this is Mrs. Johnson. This is MAT 221. We're in section 2.6 talking about the derivative at a point, and we're in video 2. Now we could also use this data and we could choose 2 points like here. We could say, well, couldn't we use the slope near 45 and 40, like using these 2 points? So it would be 340 minus 330 over 45 minus 40, which would give me approximately 2 flies per day. By the way, I want you to notice that the derivative is always a fractional unit because it talks about the rate of change, and a rate is a fractional unit here. It's change in my output units over change in my input units. So yeah, actually in this case, because we don't actually have the actual function on the curve, we could say this would be an okay estimate also because it takes the 2 points pretty close to the point of tangency. Or we could say, what about these two if we took between 40 and 35, and we would say that would be 330 minus 310 over 40 minus 35, which gives us about 4 flies per day. But notice if we went a little bit above and a little bit below, that gave us our best estimate when we're a little bit above, a little bit below the actual value we're looking at time equals 40. Any one of those could actually be a good estimate because we're just estimating in this case. So how do we estimate the derivative numerically? We take points close to the point of tangency, usually take a point a little bit above and a little bit below the point of tangency that we're talking about, and then find the slope between those 2 points. All right, so now let's do some algebraic work. Say we're given the function 1 over x, which is the hyperbolic function that is in the first and third quadrant, that x to the negative 1 power function. And I asked you to find the slope at x equals a. Whenever I asked, or anyone asks, to find the slope of the curve or find the derivative at this point, we don't have any shortcut rules yet, so we're going to have to do this the long way. So we're going to use this formula. This is the formula for the slope of the curve at any given point A. This is the derivative at a point A, where A is equal to the x value that we're looking at the point of tangency. So if we do a little algebra here, what is the value of the function? If this is my function, 1 over x, what is the value of the function at a plus h? It is simply 1 over a plus h because the function is 1 over x. So f of a plus h is equal to 1 over a plus h. What's the value of f of a? F of a is equal to 1 over a, putting it into the function, all over h. So I've now put this function, the function I'm talking about in this case is 1 over x, and I've put the formula into the function that I'm talking about. Now we have to do a little bit of algebraic manipulation here and doing a little bit with complex fractions. I'm going to multiply everything and clear my fraction a little bit by multiplying by the common denominator of a times a plus h. When I do that, the first fraction cancels the a plus h, the second fraction cancels the a. And when I reduce this, I end up getting 1 over a minus a plus h. And remember, we're distributing this so it's negative, and we're distributing over the parentheses, so minus a plus h. And then in the denominator, I have h times a plus h. Simplifying the numerator a little bit here by distributing the negative, the a's will cancel. So I get negative h over h times a plus h. But now the h's can cancel, and I'm left with just a negative 1 in the numerator, and I'm left with a times a plus h in the denominator. But if I take a limit by substitution, now that h is no longer in the denominator here, I put in 0 in for h here by a limit by substitution. The numerator is negative 1. The denominator becomes a squared. This is the general formula for the slope of this curve at any given point A. And the general derivative is kind of cool because now I can take the derivative anywhere I want by just simply plugging in what the value of a is. So if I wanted to know the slope of the curve at 2, I would simply put in 2 for a and get negative 1 over 2 squared, which is negative 1/4. If I wanted to know the slope of the curve at 10, I would simply put 10 in for a and get negative 1 over 10 squared, which is 1 over 100, negative 1 over 100. So this gives me kind of a general formula for the general derivative at any point a on the curve. So part B of this question asked, well, where is the slope equal to negative 1/4? Well, I kind of answered this question in a way, but not the only place perhaps where my curve is equal to negative 1/4. So it's asking, where does the slope equal negative 1/4? Well, I know my slope is equal to negative 1 over a squared. So what values of a will give me this slope? Actually, there are 2 correct answers. If I divide by negative 1 and then cross multiply, I get a squared equals 4. Take the square root of both sides, and I get both positive and negative 2 values of a will have a slope of negative 1/4. Now, we can have Mathematica help us find the tangent line to the curve, and we'll do a little bit of this in class when we have a chance to show how the tangent line can be drawn to the curve, although you have done a little bit of this in the manual already too, drawing a curve, a line to the curve. Now, here's the hyperbolic function 1 over x that you can see in the blue lines here. And you can see this is the tangent line to the curve at x equals negative 2. And if I were to draw over here at x equals 2, you would also see that these 2 lines would be parallel to each other. It would also have a slope of negative 1/4. All right, let's do a couple of examples here. These are from the textbook. This one says, make a table of values rounded to 2 decimal places for the function f of x equals e to the x for x equals 1, 1.5, 2, 2.5, and 3. Then use the table to answer the next 2 parts. Okay, the part B asks, find the average rate of change between x equals 1 and x equals 3. And then part C says, use your average rates of change to give me a good estimate or approximate the instantaneous rate of change at x equals 2. All right, so the first thing we're going to do is we're just going to make a table of values. Now we can do this on our calculator or we can do this on Mathematica. This is an input-output table. If x is the inputs from 1 to 3 going up by 0.5, and the output is e to the x rounded to 2 decimal places. Part B asks me to find the average rate of change between 3 and 1, x equals 1 and x equals 3. So from the table, the average rate of change is just straight up slope. So I'm going to do the output at 3 minus the output at 1 over 3 minus 1, which gives me about 8.685 as my average rate of change between these 2 points. Now I don't have any units here, so I can't do my fractional units, but it would be change in my output units over change in my input units. Part C says to use this table to get a good estimate for the instantaneous rate of change at x equals 2. Now again, this is just a table of values, so it's a numerical estimate of the derivative of the curve at x equals 2. But because we are not going to do this algebraically, we're going to do this numerically. We're going to do what we usually do is a little bit below 2 and a little bit above 2 to get a good estimate. We say that a good estimate would be a little bit above 2, which would be the output there is 12.18, a little bit below 2, which is 4.48, and then those 2 points, those inputs were at 2.5 and 1.5, which gave me about a 7.7 as my good estimate for the derivative at x equals 2. So if we just have table of values and we don't have an algebraic function that we can use the formula that we did in the last example, then we just use the data and get a little bit above and a little bit below the point where we're looking at the curve. All right, let's do a little bit of analysis here where we're not going to do some algebra. We're just going to do analysis. It says label points A, B, C, D, E, and F on the graph of y equals f of x in this figure below. So we're looking at this figure down here, which is a funky figure down here. Part A says, put point A on the curve where the derivative is negative. Now there are lots of correct answers to these, by the way, but see if you can do it without me actually doing it first. So pause for a second and say, where is it I can put a point A on this curve where the derivative will be negative? Now again, what is the derivative? The derivative is the slope of the tangent line to the curve at any given point, or the slope of the curve at any given point, or the instantaneous rate of change at any given point on the curve. I put my point A here. Now I want the derivative to be negative, which means I want the slope of my tangent line. If I were to draw the tangent line to the curve here, the tangent line to the curve would be negative. Point A could be anywhere along this branch of the curve and anywhere along this branch of the curve, because that is where the curve is decreasing and therefore where the derivative, or the slope of the curve, will be negative. Now what about point B? Point B, we want a point on the curve where the value of the function is negative. Okay, the value of the function. The value of the function is the output of the function. The output of the function is negative if the output lies below the x-axis. So there's very few points we can put in here for B, but B has to be below the x-axis. So that's one of just a few points we could put for point B. Point C is a point on the curve where the derivative is the largest. Well, let's say something is the largest if it is the most positive. So what I want to do here is I want to look where the curve has a positive slope, because the derivative is the positive. Now we don't want this, which is the local maximum or the global maximum. We want to know, where's the derivative the largest? Where's the slope the steepest? Well, here would also be positive values, and this looks a little steeper than this section. So where is the slope the steepest? The slope is the steepest right here at point C. If I drew the tangent line to the curve, it would be the steepest there. That point, by the way, has a very special point. That's called the point of inflection. It is where the rate of change is the steepest or the fastest, either in the negative or positive direction. Point D asks us to put a point on the curve where the derivative is 0. Well, a function has a 0 derivative or a 0 slope when the tangent line would be horizontal. So if I drew this tangent line, notice I would draw a horizontal line. The slope of the line would be 0. Now, where else could that actually occur? Up here, we would have a slope of 0 also, and up here, we would have a slope of 0 also. So D, there's 3 points that we could use for point D. Now, E and F asks us to put 2 different points on the curve where the derivative is about the same. Now, we could use those points we were just using, that the derivative is 0 there, derivative is 0 there, derivative is 0 here. But let's pick up 2 other points. I picked those 2 points as E and F. I forgot my F here. But notice the slope of the curve is about the same at both of those points. Notice the slope of the curve comes down with that tangent line to the curve, that tangent line that just kisses the curve at that point. And you can see at both of those points, the lines would be parallel. And remember, we know from earlier studies of math that 2 lines have the same slope. They are parallel to each other.